The heart was viewed years ago, and now we understand it so well. And that doesn't mean it isn't still complicated, but it's something that we've learned so much about. The brain has still got so far. Will we get to that level? Not in my lifetime, but it will. It's why science is fun. Be able to figure that out. My focus of the tools I've used for my entire career have been PET imaging. And even back very early on, just the ability to see inside of a live human being as their brain is functioning has just been fabulous. A key part of the brain are the connections that it makes. If you thought about the traffic patterns in a busy city, it's very crowded. At any given time, the same route may work very well or may work very, very poorly. But I think that in terms of the numbers of connections, no city comes close to the number of connections that our brains can make. In the first generation PET on X-ray films, it took 10 minutes to get each image one by one. So it took us, to get all 6 took an hour. And the image quality, the resolution on this, you can barely tell that it's a brain. And we're now at the point where we're now at 1,000-fold finer quality with the NeuroExplorer. The brain got better. But this baby is our NeuroExplorer. It was a very exciting opportunity to collaborate with United Imaging as well as with UC Davis to be able to develop this machine. And looking for something that would be the true next generation. By bringing in vectors, we're able to get that much more sensitivity, crystals, and the unique characteristics of extremely small crystals gives us very good resolution. As far as we can see right now, the best brain PET images in the world. So it's a very exciting time. The initial images we've seen have been spectacular. We're really going to be able to zoom down that much better, to look at smaller signals, to look at smaller regions of the brain, and to be able to understand how we can look at that functioning, how we can open up a door to be able to look at something that we've never looked at before. Actually, when the signal is small, you need really high sensitivity to be able to detect it. And that's one of the exciting areas that we will be doing. And I'll give an example in Alzheimer's disease. The origin of the disease is not in that hippocampus, but it's actually something called the locus coeruleus, a very small region. And if we have the ability to begin to image those very, very regions very early, how they interact, how they communicate with each other, we'll be able to get much more granularity. We can follow them much better as their disease goes on. One other dimension that's been an important part of is the collaborations with the pharmaceutical industry. We work together, we can quantitatively tell you how much of the signal is blocked by the drug. We can relate that to the drug concentration. Maybe with the kind of resolution and sensitivity we're talking about, those things will begin to happen. They'll be more diagnostically useful and more predictive. In PET, it's very important that when you see an interesting result that it gets validated, it gets replicated by a different site, with a different machine perhaps, and even with a different tracer. And we're happy, thrilled that United is building those systems for commercial purposes. We are not going to be the one NeuroExplorer in the world doing that, which honestly will be much better by having more people doing more things.